Hi there. I'm Valerio Scani, Principal Investigator and Deputy Director at the Center for Quantum Technologies in Singapore. Ever wondered what quantum scientists actually do? You're in the right place. Learn about ongoing quantum research, what inspires us, and a day in our lives inside and outside the lab. Tap the buttons below to explore or input your questions in the tablet next to me. Let's dive into the quantum realm, one question at a time.
It all started when I was in junior college and I attended an outreach program called QCamp hosted by CQT. While at QCamp, I attended a lecture by Professor Valerio on the implications of quantum causality, and that really inspired me to pursue my bachelor's degree in physics. And now I'm here in CQT doing my PhD in quantum sciences.
When I was an undergraduate in 1993, a friend of mine introduced me to Bell non-locality, and this phenomenon really captivated me because it showed that there is true randomness in nature. At the time, these topics were not part of the normal syllabus. In fact, I didn't study any of these things in my undergraduate courses, and because this was long before quantum computing gained traction. After that, I decided to devote my life to study this phenomena, and I was very lucky to be able to contribute. I even eventually ended up authoring one of the main books on the subject.
I like the fact that quantum science invites us to rethink the foundations of technology and even our reality more broadly. It challenges our intuition, reshapes logic, and offers a radically different lens on how the universe can compute and can learn. I'm especially motivated by the chance to contribute to a field that's still so young, where fundamental discoveries are potentially still ahead.
The counterintuitiveness of quantum is fascinating, like entanglement and superposition. When you think deeply about it, it doesn't make sense. But mathematically, it's rigorous. And in the lab, we observe that what quantum mechanics predicted is correct. The moment we successfully make a device or measure something expected or even unexpected, it's full of joy and surprises.
Hi, I'm Diron Spira. I am a research fellow at CQT. I work at the intersection of quantum computing, machine learning, and theoretical computer science. My research asks the question, how do quantum systems learn? Like humans or machines learn, but using the strange rules of quantum physics. I build algorithms and develop theory to understand learning in the quantum world, not only to speed up AI, but to rethink what intelligence might look like when powered by quantum mechanics. The goal is to design fundamentally new approaches to learning that use the elegant behavior of quantum systems. This could help eventually with scientific discovery and complex simulations that today's computers struggle with, such as designing new materials, improving sustainability, or with broader scientific understanding.
My name is Sheikh Abdullah, and I'm a PhD student at the Center for Quantum Technologies. My research involves bringing quantum communications into space. Soon, we will be having quantum satellites that communicate between distant observers using ground stations similar to this one that support quantum communication on a global scale. This research is highly interdisciplinary, having disciplines including aerospace engineering, astrodynamics, material science, and quantum optics.
Hi, I'm Valerio Scani, a Principal Investigator and the Deputy Director of CQT. For many years in my research, I've been asking which phenomena can be taken as signatures of quantum behavior. When I say this, maybe many of you are thinking of phenomena in which particles behave like waves, like the famous interference patterns observed for electrons, atoms, neutrons, and more recently even with big molecules. And indeed, these phenomena cannot be reproduced with classical particles or classical waves. However, they can be simulated by a classical computer. So we have been asking, are there quantum phenomena that cannot be simulated even with a classical computer? And well, the answer depends on the power you want to give to your computer, but there is a remarkable phenomenon called Bell non-locality that cannot be simulated with any classical computer, however powerful. Actually, it requires two computers, two objects, separated so that they cannot communicate. This phenomenon was first demonstrated in the labs in the 1980s and has been the object of the 2022 Nobel Prize in Physics.
Hi, I'm Didru. I'm an assistant professor at NUS, a research scientist at A*STAR, and a CQT fellow. My research is about building chips to process quantum information. We use photons, which are elementary particles of light, to carry information. On our chips, we have photonic circuits made of wires that are about 100 times narrower than human hair. Just like metal wires guiding electrical currents, these photonic wires guide light. What's more interesting is that we make these wires out of special nonlinear materials. When we shine laser light into them, they can help us to produce pairs of photons that are like twin sisters. These sister photons share strong correlations even when we separate them far apart. We call them entangled photons. And this is a common quantum resource that we make use. We can produce many of these photons on a single chip. We control them, let them interact, and detect the outcome. This process is equivalent to solving certain complex mathematical problems that are relevant to logistics optimization, cryptography, and even drug discoveries.
No 2 days are quite the same, but most of my time is spent thinking either about abstract problems in theory or how to design algorithms and learning models that reflect quantum behavior. I read research papers, write proofs and code, and collaborate with other researchers, often across disciplines and continents. Some days are spent mentoring students or whiteboarding with colleagues, and in the end it's a mix of immediate problem solving and big picture exploration.
My main task is to conduct research with the help of a team of young people, very motivated. Most of my day is spent thinking of projects, reading drafts of papers, and discussing with colleagues all over the world. Also, very often I have to travel or to entertain international collaborations. Besides this research activity, I have to teach. I'm a member of a university. In particular, being deputy director of CQT does require some time for administration and service.
Just like everybody else, I start my day with a fresh cup of coffee. Then I read some latest research papers. Then I discuss with my students. We discuss how to make photonic chips in the clean room. During the semester, I have to teach. I teach on quantum science and the semiconductors. The rest of the day, I would spend time doing experiments in the lab with my students.
I start my day at around sunset. At 7 p.m. is when satellites are most visible from our laboratory. So I will do my experiments until about 10 p.m., after which I will head back to my office to read papers and do other administrative works. I will return at about sunrise to do my next round of experiments, and I will stay a bit late to wait for my colleagues to come in, and then I'll call it a day.